Hey everyone, my name's Zach Hammer. I am an engineer on the platform engineering team at SeatGeek, and today I'm going to be talking about getting creative with tracing. Now, just to cover the basics, this is SeatGeek where I work. We're a company with offices all over the world with a headquarters in New York where I'm based out of, although currently I'm working remotely. And the goal of our company is to help the world experience more live. That's either on the consumer side with the SeatGeek app, which you may have used to buy or sell tickets to concerts, sports events, or other forms of live entertainment. And we also work on the box office side, where we provide ticketing software to a bunch of teams and organizations, both in the US and across the world. Today, though, I am not here to talk about ticketing. I'm here to talk about tracing, and specifically how we can take the tracing tools that Datadog gives us and build out really creative applications of tracing for our organizations. Now, if you've used Datadog tracing before, you'll know that you get a lot of power out of the box instrumentation of tracing for a service. And when I say out of the box instrumentation, it's really not too much work to get your app emitting tracing data to Datadog. This is how essentially you do it for a Python app. You'd say pip install ddtrace, I want the Datadog tracing library. And then instead of running your Python interpreter with your application directly, you're going to wrap it in this tool called ddtrace run. That's going to do a bunch of that heavy lifting and bootstrapping to patch out some commonly used libraries within Python and get the tracer running in the background so that your application is constantly sending that tracing data to Datadog. And you do that, ship your code, and if your environment's configured correctly, you get a lot of power just with that. You get flame graphs, you get service maps, app analytics, and more. And what I'm going to talk about today is how we at SeatGeek saw that default Datadog setup not as the end game of how we want to trace our applications, but as a foundation upon which we've built some really creative uses of the Datadog tracing toolkit to kind of custom tailor tracing to what our organization needs in terms of observability into our tech stack. The three topics I'm going to cover are: one, tracing asynchronous workloads; two, unifying our tracing specification; and three, which kind of piggybacks on the previous two, not just writing out a tracing specification saying this is how your app should emit data, but also building a tool that will say this is how your app should emit data, and we're going to cover all the heavy lifting of doing those acceptance tests to make sure your app is emitting data in a way that we're comfortable with once you're on prod. So just to get into it, we're going to start with tracing asynchronous workloads. And if you've used Datadog tracing or really any tracing solution, you're probably very familiar with the use case of tracing synchronous requests. And what this really is saying I have some endpoint on an API or a service, and it is receiving requests, and those requests take some amount of time to process and respond to. And what I want to get out of tracing is to see where different parts of that request are allocating their work and what's happening in those workloads within the requests being processed. To get a SeatGeek view on that, let's say we have this ticket ingestions endpoint where somebody can upload a PDF to SeatGeek that they've gotten outside of the SeatGeek ecosystem and say, I want to have this ticket in my SeatGeek wallet, in my SeatGeek account. What's that going to look like from a trace perspective? Well, first we'll see that we do a quick request to Redis to do some authorization on the user. Then we have this span that's manually instrumented in Python where we decode our ticket, and that's going to be parsing the PDF, figuring out the seat, row, event title, artist name in that ticket PDF. And once we've gotten the information we want, we'll take that PDF, post it to an S3 bucket, and then dump the information we've decoded from that ticket into Postgres. This works great for what it does. You can see exactly what's happening as this one endpoint processes. But the problem with it, which some of you may already be thinking, is this is not how all of our endpoints and our applications behave. And this is actually not really how our ticket ingestions endpoint behaves. It looks a little bit more like this, where somebody submits that ticket PDF, we're going to do that Redis authorization lookup, but then pretty quickly what we're going to do is take that PDF, dump it into an S3 bucket, write some preliminary data into Postgres, and then we use Rabbit as our message broker. And we'll say, hey, Rabbit, we have this ticket that needs to be ingested, and then eventually some worker is going to consume that message. It's going to pull that PDF down from S3, do all that decoding work, and then in this whole asynchronous workload, take what it's learned from that PDF and dump it into our Postgres database. What we realized pretty early on is that the default out-of-the-box instrumentation for tracing did not cover these asynchronous workloads. And what happened with us is we were so excited about all of the awesome visibility that Datadog tracing was giving us into our synchronous workloads that we really wanted to extend that visibility into our async workloads that are so core both to our business and to how our applications behave. The path for us was pretty straightforward. We looked in all of the ddtrace libraries for the languages we use and saw that there wasn't a community or Datadog supported RabbitMQ integration for tracing, and we decided to go and build our own. And this was quite new to us, but what's really great about working within the Datadog tracing ecosystem is you basically have dozens, if not like 100 examples of how to write your own custom Datadog tracing integrations. And that's because every single language's ddtrace library has a bunch of packages of community-supported integrations into tracing. And just because RabbitMQ wasn't there didn't mean that we couldn't go and see, oh, this is how tracing's done for Asyncio, this is how tracing's done for Botocore, and take a lot of those lessons and bring it over to write our own instrumentation of tracing Rabbit messages. What we did at first was we said, we have this Python app that we know is pretty central to SeatGeek's behavior. It does a lot in terms of both publishing to queues and consuming messages from Rabbit. Let's just go in and hack around, see how it's publishing and consuming messages, and just tweak it a little bit so that at a very bare minimum, we have this proof of concept where Datadog tracing IDs are being sent over and consumed from Rabbit messages. And what happened was we did that. We shipped it after a few iterations of getting it right, and we got some really cool trace flame graph breakdowns. This also happens to be the part of COVID where I was feeling very deprived of all of the culture and art that you get from living in New York City when you can go outdoors. I was stuck inside my apartment, and I kind of took these flame graphs that in the asynchronous world have a much higher cardinality of what they can really look like and display, and took them as my own little art exhibit. This is the first one that I call Infinite Staircase. What essentially is happening here is we have some bad retry behavior on a consumer where some condition isn't met that the message can be consumed, and for like 5 minutes, that queue just repeatedly tries to re-queue the message with really no back off or anything like that. It ended up looking quite funny. This is a very small snapshot of it, but you can see there were over 1,000 spans, and you can scroll through this for a very, very long time. And this was also a bug that a lot of us had been aware of whenever we got really close to working with this consumer. But since it ultimately self-resolved and none of us really wanted to scrap through a bunch of logs to be like, this is exactly what's going on here, we just kind of left it as is. But it was really funny to share and say like, oh, this is actually what's happening when this one consumer that we know of is kind of on the fritz for a few minutes. The other piece that I coined is jellyfish in a tank. I just named it that because this reminds me a lot of when I was a kid and I went to the aquarium and saw all the bioluminescent jellyfish floating around in that dark tank. And what's happening here is we have some workload that's dumping a ton of messages into a Rabbit queue. And I think this is something like finding out from a broker that a listing price has changed, so we have to update all these prices across our system. And what you can see is since this RabbitMQ queue at the moment is quite bloated, these messages are consumed by workers, but they're consumed at this kind of sporadic interval. So it's only like 40 seconds in that one of these messages that was published only a few milliseconds into the workload, it's actually consumed. And under that, you see all the database calls and other work that that consumer is doing. And we had these flame graphs, but also a bunch of more conventional flame graphs that showed our apps behaving as we would expect them to behave. And we were quite excited about it. And we shared it with our app teams. And what really happened was folks said, hey, you were able to set up Datadog tracing for Rabbit on this one Python application. Would you be able to roll it out to all of our Python applications, since hopefully you can reuse some of that code and get that out quite quickly to us? And we were really excited about this idea. But this kind of leads us into our first big learning about rolling out our own creative applications of tracing at SeatGeek, which was the importance of unifying our tracing schema. Because what happens when we get this request to roll out distributed Rabbit tracing to all of our Python applications is we stop and we think and we say, okay, this is moving from an experimental POC to a real kind of production shipment of Rabbit tracing within Python. What do we want to get right? And the two things that we really wanted to get right are, one, we didn't just want to be percolating around these tracing IDs in our Rabbit messages. We wanted like a really rich schema of data that's being sent with our Rabbit libraries where we could say, hey, we want to put an SLO on messages being consumed by the tickets ingesting routing key. And we want to see across all of our applications that may be written in different languages, how long does it take and what's happening when these applications are responding to this routing key. The second thing, in addition to having a rich schema of data that we were shipping with these trace messages, is we really wanted this behavior to be replicated almost exactly on every single Python app we have, because the whole value of tracing is that you get all this consolidated information from a bunch of different applications doing different things, possibly written in different languages. For the first part of that, for having a rich schema, what we did was a few of us just really looked through the APM glossary and all the information that Datadog had shared, saying like, this is the core schema for how tracing data is emitted from your applications to Datadog. And we were able to say, you know, instead of building in parallel to this schema they've already rolled out, and instead of maybe even building against it in that all these tags we're emitting conflict with the default Datadog tracing integrations, we want to build on top of it so it's a really cohesive experience to say, oh, I know how to do really interesting queries on all of my HTTP clients. I, as a developer, without having too much overhead, should be able to translate that kind of intuitive understanding of how to use Datadog tracing into how I'm going to look up behavior of our Rabbit clients. And in terms of having replicatable ways that this information is emitted, that was quite easy since we were all within the Python ecosystem, and it really fit in with our ideal on how we work on our team, which is we should be able to go into the Rabbit libraries that these Python apps are using, have one shared solution for how we cover this tracing, bump the versions of those libraries, and our application developers really shouldn't even have to notice, besides like bumping some version of a pip requirement, that they are now shipping Rabbit tracing data to Datadog. What happened though here is we were able to build this Python library. We did a lot of work to get the schema right and the way it emitted data, and folks got really excited about it. And then suddenly what happens is we have people on teams that build .NET apps and teams that build Golang apps, and they say, hey, what you've done in Python is great. And we just had a bug today where we had some messages that we expected to be being shipped to a RabbitMQ. We didn't see those being consumed by any of our consumers, and we took a few hours to figure out what was actually happening and going wrong, whereas if we had this distributed Rabbit tracing, we probably would have been able to do that in maybe just a few minutes. So our team says, okay, you know, we're really excited about continuing to roll this out, but now we have a new problem, which is we can't just have this whole schema live within this one PR to our Rabbit tracing library in Python. What we did was we went into that PR where we made all these decisions on how we're going to ship this Rabbit data, and we extracted out a document that really documents how we expect applications, and we're already having Python applications ship tracing data about Rabbit to Datadog. This is just a small part of that where we say when we're doing publishes, we're going to call those spans. The operation name is going to be RabbitMQ.publish. Our resource is going to be the exchange and the routing key. And then the service name is going to be whatever service, whatever cluster host name we are shipping those Rabbit messages to. And we basically put together this whole document and shared it with our .NET and Golang teams and said, we can support you a bit, build a library that handles Rabbit tracing the way we've laid out here, and you should be good to go. Now, what we realized here is, one, this was taking quite a bit of time because everybody had to start from scratch, rebuilding this tracing library from the ground up. And the second thing that was quite difficult is we realized very early on that this was a fragile solution. And why is it fragile? Well, what happens if we want to update one of the key names and our key value pairs we're sending to Datadog? We don't have one centralized place where this specification lives. We have this document that's inevitably going to get outdated. People are going to make changes to the .NET library, not to the Python library. And the whole goal of having a unified way in which we emit tracing data from our applications to Datadog is going to very soon kind of become a mess and go in a bunch of divergent directions. And that's where we got really excited about this idea of specification testing. And the question we really asked is, What if our tracing specification was not just a document that said, hey, here's how we expect you to trace Datadog requests on your Rabbit queues? What if we had a document, but it also came with a tool that you could run on your machine or run in CI, and it would essentially cover a lot of the overhead of doing these high-level acceptance tests that make sure your application follows the specification by actually checking the traces it emits when it receives a Rabbit message. What was really exciting about this idea of having one centralized specification that not just specified how we expect apps to be emitting traces to Datadog, but also test that those apps are emitting traces correctly, is that it opened up a whole new development flow for people who want to get Datadog tracing into their apps. Let's say we have somebody on data science that wants to consume apps from one of our message queues to do some on-the-fly price calculations, and they really want to get that Datadog Rabbit tracing so they can see what's going on inside of their consumer. Well, we could say, hey, here's a specification for how to set up some Java library to consume messages and send traces based on those messages. And one, you know that that specification is up to date because it's being used in the CI pipelines of our Python and our .NET and our Golang tools that are all being shipped to prod currently. And two, you just gotten a huge chunk of your work taken care of for you because you don't need to totally understand all the intrinsics of Datadog tracing. You just need to build out your tool well enough that it can consume messages from Rabbit and pass our Rabbit tracing acceptance tests, and you should be pretty much good to ship and expect your data to show up how you're used to it showing up in different parts of our tech stack. Now, this is a tool we're still working on, and essentially the idea here is that we're building on top of Cucumber tests. If you're unfamiliar with Cucumber, Cucumber is this whole world of testing tools and a language that allows you to write really clear, high-level acceptance tests and specifications for how you expect your application or tool or website to behave. Then you can take that specification that's really easily shared and human readable, hook it into some underlying language driver. For instance, we're using Godog, which is the Cucumber driver for Golang, and actually test that that specification is being followed by your application. So this is just an example feature that we may have. We could say, hey, here's the specification for our trace Rabbit consumer. All we want from you is to take your Rabbit consuming library and put together a tiny app, and all that really has to do is connect to the Rabbit connection URL environment variable, as you would expect to do in our production environment, and then consume messages from this queue called test message queue. That's all you have to do on your end. We can give some information that's actually going to be used in our tests about how we expect parts of the environment to be set up. We could say, when we execute that application, we're going to have this key DD service, which is going to have the value my consumer, which is also going to be the case in your production setup. Then when we start your Rabbit consumer, we're going to send some messages to that message queue. And one of those messages is going to be to the test message queue with the trace ID 111 and the parent ID 222. And we expect on your end, when you receive those messages, to emit the following spans to Datadog. And what we're actually doing here is through environment and variable injection, we are giving a different agent host than the one that would automatically be registered. We have our own little Go routine running on the Golang side that's listening to those messages being sent to that kind of mock Datadog agent. And we're parsing those spans that we are intercepting and saying, are they meeting this specification that we've outlined? We want it to have the operation name RabbitMQ.consume. We want it to have the service myConsumer. Because we've sent these two IDs over the wire, we expect that span to have the trace ID 111, which is our root span, and the parent ID 222, which is what we said, the parent ID coming from our messages. And we can put in really a ton of different information. We could say, hey, part of our custom specification is you always say the queue you're consuming from. And here we want to make sure that your application is emitting this data that you're consuming from the RabbitMQ queue called test message queue. And again, this is really quite a simple specification for people to look at. They say, you know, I know what you're expecting of me. I know what I'm supposed to develop for, and I can test to make sure my application is sending those Datadog telemetry metrics correctly. Now, again, this is something we're still working on, but the end goal is a really ideal state where we can have a great workflow where we say, hey, I know a lot of folks are interested in tracing their cron jobs, and we're excited about that too. And what we've done is written up a specification for how we expect apps to emit cron jobs to Datadog through Datadog tracing. And let's say you're a .NET team. All you have to do to emit your cron job traces is pull down our specification, use that tool to build out your own cron job tracer tool, make sure it matches our specification, ship it to prod, and you will be all good to go. We'll be ready to consume messages and telemetry in the format you're providing, and you'll not only have this set up correctly for .NET, but it's going to integrate really smoothly with all the cron jobs that are running, not just in .NET, but across our entire tech stack at SeatGeek. So that's just some of the ways we've been getting creative with tracing at SeatGeek. If you are excited about some of the work we're doing here, one, feel free to reach out to me, but two, we are hiring. You can go to SeatGeek.com/jobs to get all the information on all the roles we have available. We're really excited for folks to join, not just our platform team, but any team at SeatGeek overall. And thank you for listening.